We're now going to look at current in a little more detail. We're again looking at this blown up section, portion of a wire that's carrying the flow of charge, and you can see we have the cross-sectional area A. The generic length of the wire we're going to look at and say is delta x, and we are right away defining this scripty n. So roll it up here a little bit. It's a scripty n, which is the number density of charge carriers that are flowing in the wire. So for us, of course, the charge carriers are positive, but it would correspond to the equal number of electrons if it was electron current flowing in the other direction. Now, we have to be a little careful with units here because our number density is a number. So if it was 10,000 electrons or 10,000 conventional charge carriers, that's just a number. So the top part is always just a number. The units come from the per unit volume. So that's our meters cubed down here at the bottom. So we have a little bit of manipulation of some variables and some math to do to get a nice convenient equation for the current, the coulombs per second of charge flowing through the wire at any given point in time. So we just look at the volume first as the cross-sectional area times the distance delta x. That gives us our meters cubed, right? We have meters squared for cross-sectional area, meters for length. So we have our volume. Velocity is, of course, distance over time. So we have our drift velocity is delta x over delta t. Our delta x we are going to take a look at by rearranging in this equation. So the delta x is v times delta t. We bring the delta t up, so that's where we get our delta x equation from. The delta x equation here we are going to plug in up here to get a new volume expression. So we get an expression for the volume based on the cross-sectional area, v drift times delta t. We are then going back to our initial equation. So we are going to take, I'm going to box it. We're going to take this volume equation. We are going to plug it in up here and take delta, the volume times the script n. So we have the script n times this boxed volume. And that is going to give us the number of free Qs. So the number of free Qs, right, it's going to be a big number, but it's script n times this new mush of variables, a velocity times delta t. So the total charge in coulombs then, we have to take each of those free Qs and multiply it by 1.6 times 10 to the minus 19. So multiply each of them by 1.6 times 10 to the 19, and we get the total number of coulombs flowing through the wire. And when we take the coulombs per second divided by the delta t, we lose the delta t, and we get the current as the charge on the electron, 1.6 times 10 to the minus 19, the number density, script n, cross-sectional area A times the drift velocity V. So this is an equation we do want to memorize, that the current, the flow of charge at this, at least for us, the most microscopic level that we are going to look at in a kind of an atomic molecular way, the current will equal QNAV QNAV. So that is how I remember it. The Navy, the United States Navy, abbreviates everything, even the word Navy. So they will abbreviate the word Navy to NAV. So I always remember this as kind of a official Navy sounding term, QNAV. So I equals QNAV. So however you remember it, that is fine. If QNAV helps you out, then that is wonderful. Again, I'm zooming back out here. You can pause the video, get the annotations down. You do not need to memorize the derivations for this page, but I did want you to see that QNAV comes from a logical progression of analysis looking at a section of the wire. and we will go on from here.